And let me restart the timer and we'll go over the last part of the lecture. Okay, so this is the section on indicators. And indicators themselves are acids and bases that react with the hydronium ions and the hydroxyl ions that are present in solution. And therefore, when they react, they form new substances, and the new substances happen to have different colors. So what you're going to see is going to be at a certain pH, the indicator is going to change colors, and that's because it's being protonated or deprotonated. So this is a picture of the different indicators with different changes in color. So the changes in color depend on the nature of the actual compound. They are usually organic compounds, and there are characteristics to the color of those compounds when they gain protons or lose protons. So notice here you have a pH scale. So this is the acidic part of the pH scale. This is the basic part of the pH scale. 7 will be the neutral point. And notice that these are changing in color. So let's look at methyl orange, for example. Methyl orange will be red when it's in acidic solution, means it's protonated. So, and when it turns into its conjugate base, it deprotonates, then it's going to change to yellow. And in between, in this range here, from about 3, let me put the number 3 here, and the number here is like 4.8. Between 3 and 4.8 is going to start changing colors. So these are not very sharp. None of these is kind of a sequence, and you have used phenolphthalein already, probably in the General Chemistry 1 lab. And notice this goes from colorless to red. So, and again, and it's about 8. See, so it's about 9. And this one is going to be almost basically, let me see, 0, 1, 2, 3, 4, 5, 6, 7, 8. No, it's 8. This scale is kind of funny. Notice that this one, they get displaced as you go back, as you go follow. So 8, this is 8 and this is 9. So this is 8 when it's still colorless, but if you start going beyond 8 into 9, it's going to change colors. And by 10, it would have changed colors. Now, if you remember phenolphthalein in the laboratory, when you use it, it just went very sharply to very strong color. And that is because you're adding, you were adding a base, and just one drop of the base can cause a lot of the change in the pH. Almost from 8 to 2 is 2 units. Though that's, remember the pH scale is exponents of 10. So 2 units of pH is 10 to the 2 or 100 times more basic. So that is because you were not using a buffer. It was just an acid-base titration. It would be instead of your titration that you're doing, it would be a buffer. It would change very little with one drop. But because there is no acid-base effect there, it changes dramatically. Okay, so here you can have, if you can see, this spans the concentration from 0 to almost 12. So you can have indicators that actually allow you to find any pH that you want to target. This Thymol blue, the only thing that is interesting about it, it has 2 colors. So this must be a diprotic. Diprotic means that it has 2 hydrogens. So it has a first dissociation for the first hydrogen and the second dissociation. So that's where you see here 2 different color changes. To be good indicators, they have to be fairly water soluble. They have to be weak acids and weak bases because it's still, yes, and it is an equilibrium. So it has to change colors with respect to the pH. So they are weak acids, and then the protonated and the deprotonated species have to have different colors. So they have to be a changing color. Okay. So, and the pH in which they're going to be, right, means in the middle here of these ones, and you're in the middle of these bands, you are their pKa. So they are just acid bases again. Okay, so let's look at a titration. I think that this is the most important and interesting part of this chapter. And that is when you do a titration, what you have is a burette here that you're going to use to deliver the acid or the base. And in the laboratory, we're going to have a probe. We're going to have our lab quest. Instead of this one, we have our lab quest. So this will be kind of our lab quest. And there'll be a probe that is going to be inserted into the solution. And we're going to measure the pH. So when we look at the phenomenon, we're going to look at an acid-base titration. And the acid-base titration could be a strong acid with a strong base. In that case, there's no buffering effect. There's the acid and the base reacting to form sodium chloride. So when we have added enough acid to neutralize the base, means pH 7, we are going to actually have a solution that contains only the sodium chloride. Notice that this reaction here, let me change to yet a different color, if I can. Yep. This reaction here only goes in one direction. And if it goes only in one direction, means it's not an equilibrium. The pH for the neutral salt is going to be 7. We can tell that because, again, acid-base properties of salt, we discussed it last time. You have sodium ions. You have to look at the ions and think about the parents. So the parent of sodium is sodium hydroxide. The parent of HCl, the negative ions, you add hydrogen, and so you have HCl. For the positive ions, you add hydroxides. Strong base, and this is a strong acid. And strong acid and strong base, their baby, so to speak, NaCl, is going to be neither acidic nor basic because both are strong, they cancel out each other, and it's going to be neutral. So NaCl is a neutral salt, and the pH at the end point is going to be 7. Now for this sodium hydroxide and HCl titrations, what we're using is phenolphthalein. Let's look at phenolphthalein because that is interesting to look at. We're using this, and notice that this 7 is here. This is 7. So when we start seeing, we remember you probably were told this very many times, you want to have the palest pink solution that you have. Why? Because even when you are pale, that means that you have over-titrated. You have brought the pH all the way to 8, and that means that you have gone over. So when you're using an indicator that is highly colored, then you want to, and especially when your changing color starts 1 pH beyond the endpoint, you want to be really at the palest pink that you can. And even if you're at the palest pink, still you have over-titrated that. Now, it doesn't take that much. If you remember, half a drop will make a big difference in the pH because it will change a lot the color. So it doesn't really affect the accuracy of your measurement, but this explains why we wanted the palest color of pink as possible when you do a titration. Acid-base titration that has a pH of 7 as the final point. When using phenolphthalein, you want it as pale as possible because even when it's very pale, you have gone over it. Okay. So when you use this kind of setup here, what you're going to do is measure the pH. So you do not need an indicator. An indicator is something that is going to allow you to be able to judge what the pH is without. So we can say instead of indicator, we can use a pH meter and measure the pH. The indicators are just indicators of pH values, and you can see there for every pH you have a different indicator. When we're using a probe, a pH probe, then we are actually reading the pH of the solution. Okay, so we saw that the reaction of HCl and NaOH, which are strong acid and strong base, they give you a neutral salt. So the endpoint is expected to be at 7, pH of 7. However, if you have a weak acid and a strong base, the salt is going to be, again, acidic or basic? Who can tell me? I'm waiting. Do I have my volume up? Yeah, I do have my volume up. So I'm going to go just on my own. You have a weak acid and a strong base. So the strong tendency is going to dominate the salt that is produced by this reaction, and means that it's going to be basic. If it's basic, that means when you have the salt, the pH is not going to be 7, but it's going to be beyond 7. Because when you have neutralized completely the acid and the base, you have a salt that is itself a base, which means that the pH is going to be larger than 7. So at the end point, you'll have the pH larger than 7. Can you use phenolphthalein? It depends on where the pH is. Yes, if it's between 7 and 8, still phenolphthalein will work, because when you get to 8, you're going to start seeing the pink color. If it goes beyond, then you have to use a different indicator. Okay, so again, where is going to be the endpoint? So just think about it when you are titrating. So let's say you have your acetic acid here. So this is your beaker. Let's say you're doing the titration. This is your solution. And you have HA here. And you have your burette. And your burette is dispensing NaOH. So you have that. And the NaOH is going in. What you're going to find, what you're going to be producing is going to be CH3, COO minus ions, and sodium ions. And therefore, you're going to be producing the conjugate of the weak acid, the conjugate base. And the conjugate base and the weak acid and its conjugate base is going to have a buffering effect. So there's going to be a point halfway through the titration when you have neutralized half of the acid, and half of the acid has gone to produce the base. So you have 0.5 of the acid, and you have 0.5 of the base. If you look, and you have a buffer, and at that point you have equal concentrations of the base and its conjugate acid, and therefore the ratio is going to be exactly 1. And if exactly 1, the logarithm of this is 0, and the pH is going to be equal to the pKa. So if you can stop at the half point, you can actually find experimentally what the Ka value is for the weak acid you are titrating. And that is a powerful technique to be able to do that. So here we have two acids. being titrated with a base. So you have the acid in the beaker. So let me write again the beaker with the acid. And you're going to add the NaOH. And these are two different titrations of OH. Let me erase it. So you're going to have two different titrations. The first one is the red one, which is an HCl. And the second one is the blue one, which is a weak acid, in this case, acetic acid. So acetic acid is the blue one. You can see here, the red one represents HCl. So the titrant, which is this one here, the one that is being added is called a titrant. So it's the solution used to do the titration. And that's 0.1 molar NaOH. So let's look first at HCl when there is no buffer. So when there is no buffer, we see that the reaction will start a given pH. And as we add the base, it starts to deviate more and more, although I'm writing it backwards. So I'm going to start very little deviation, and as you add more base, let me see if I can draw a straight line here. Yeah, not a straight line, but you can see that the distance here between these points actually increases all the time. And that's characteristic of a strong acid, strong base. Strong base is NaOH reacting with the strong acid HCl. So that's the red. So HCl with NaOH. Okay, so now let's look at the base. So we have the weak acid, excuse me, not the base, the acid. Weak acid, which is the blue. And notice here we start at a given point, and there is a very quick change as we add the base. So there's going to be grows a lot. But then at this point, there's less and less growth. So these arrows here are they're not growing as much. They're going to grow the least at this point. And they keep growing, but not as much. And there's going to be a point in which the pH shuts up, and that's the equivalence point. And the equivalence point for this reaction is here. The equivalence point for the HCl is here. So this corresponds to exactly 7, the middle. The one for the acetic acid, let me switch to blue, corresponds to 8.8, 8.7. Yep, 8.73 actually is given here. So that is because at this point you have only NaCH3COO, salt in aqueous solution. And that's a basic solution. So first difference, the final point is going to be different from HCl, which is 7, to a basic pH because this is a basic salt. Second difference is going to be how the growth is going. So compare here the orange arrows here with the green arrows here. And you can see that the behavior is different. First, it goes up a lot, then it kind of tapers down. So the slope is going to be almost 0. And eventually, just like in the red, there's going to be a point in which it shoots up. Notice here the end point is at 20 for both of them. Halfway through the reaction, you have what is called the midpoint. And the midpoint for a weak acid, when you see this behavior here, so let me write it here again. Let me draw it. Yeah, let me draw it here. It's okay. you'll see this effect. That's characteristic of a weak acid. When you see this effect, that's characteristic of a strong acid, because there is no buffering effect. This slope is almost continues the same. While here, the slope starts high, then it goes down, and then starts to take off again. And the middle of this, middle of the endpoint, so this is the endpoint, halfway through, is the flattest point. It's actually an inflection point. If you have taken math and talked about inflection points in a curve, it is an inflection point in this curve. This if we look in here, this curve here again, this one is concave pointing down, and this is concave pointing up. So that would be the overall trend like this. And this is the inflection point. So at the inflection point is the halfway of the titration, and that can be found if you go to the endpoint. You just take the volume here on this scale and go halfway, trace it up, and that will give you the pKa. So this is the pKa. This is getting very busy. Let me erase some of these lines. Yeah, let me erase some of these. So if you come, let's go this way. You go down to the endpoint to get the volume, then you go half. So you go half of the volume, and then you go up again to the line, and then you go to the pH scale. At this point, pH is equal to pKa. So at this point here, pH is equal to pKa, and you can read the pKa here. So this value here is going to be the pKa that you can read, and therefore find out what the pKa, or the dissociation constant, is for any weak acid if you have a pH meter and do what is called a potentiometric titration. Potentiometry is pH probe. That's the technical name for pH probe, or the physical phenomenon that you use to calculate the pH. So means a potentiometric titration is done using a pH probe. And so you can determine the pKa, you can determine the endpoint, you can determine whether it's a weak acid or a strong acid. Notice that both curves, after you go through the endpoint, in both cases, they follow this exactly the same pathway. Why? Because at that point, once you have neutralized all the acid, the only thing you're adding once you get to the endpoint is going to be excess base. And the excess base is going to have exactly the same amount. So there is no excess base here, but once you start from here on, you'll have excess base. And the two curves look exactly the same because they are only the result of the excess base, in this case hydroxide ions, being dissolved into the solution of the neutral or the neutralized solution with salts. Okay, so you can do this with ammonia, for example, or you can and compare ammonia to HCl. Here we have ammonia being titrated, looks, with HCl, and again you have a weak base, strong acid, and therefore the salt is going to be strong. You're going to go with the strong, the trait, so it's going to be acidic. It's not going to be a strong acid, it's just going to be acidic. Which is going to be the species acidic? Again, acid-base properties of salt. You have NH4 ions and Cl ions, Cl minus ions. So I shouldn't have drawn it there. Let me move it a little bit down. Okay, so the NH4 plus ions are going to, they come from NH3. Oops. That's the conjugate base. So this is the base, and this is the acid. Let me write it in red. So this is the base for the chloride. So let me Cl minus, and HCl is going to be the acid. Again, this is strong, so this one doesn't go that way, it only goes this way, while this one here can go, is a weak and can go both ways. So this is an acidic solution here, and the equivalence point then will be less than 7. The pH at the end equivalence point pH is going to be less than 7. At the midpoint, you can use this, the concentration of the acid and the base are going to be the same. Why? Because at the midpoint, you have neutralized half. So half of, if you're neutralizing an acid, half of the acid has gone to the weak, to the conjugate base. If you're neutralizing a base, half of the acid, half of the base has gone to the conjugate acid, and therefore your concentration of acid and base at the midpoint are going to be equal, and this number here is going to be 1, and the logarithm, this number here, is going to be 0, and therefore the pH is going to be equal to the pKa. And here you have a titration. Again, this one is a base. How do I know this? The blue one is a base? Just by not even looking at the fact that of the data that is here, because of the shape. It starts on the basic end of the pH scale, right? This is the basic. This is neutral point, and this is acidic. So I know that these two solutions are basic because they start on basic pH. This is before you're adding any of the titrants. So these are bases. This one is a weak, and this one is a strong. Right? And so this is a weak base, and this is a strong base. And the equivalence point here is 7. And if they're using the same thing, which means that a strong base reacting with a strong acid, so titrated with strong acid. And all this I'm deducing just by the shapes of the curves. And the pH at the endpoint, which is marked here, being 7, which means that this is a strong acid, and the titrant, so the titrant, and please know all these words, titrant is going to be a strong acid. Again, for the strong base, there is no equilibrium, but for the weak base, there's going to be a pKa associated with a pKb actually associated with this. So again, we'll go 20 as the final volume, and then we come up here and go to the midpoint and read here. What I'm going to read is the pKb. Okay, so let's see how far we're in time. Okay, so we have another maybe 5 minutes. Remember that the Kahoot for Thursdays is going to be online. I will put them online and send you an email. And it's going to be due on Monday. Okay. Let me see. Let me pick here. This is the practice exercise. And then we're going into the second part. So this is going to be the next time. We're going to look at, we're going to look at another example of acid-base titrations. In this one, which we have 2 curves. And so there's 2 endpoints. And 2 endpoints is again that there's 2 hydrogens being being dissociated in this case. This is a base. So I know that this is a dissociation of a base, and there are two endpoints. You can see it by the shape of the curves. So there's going to be two hydrogens. So this is the base, or the conjugate acid of this base is going to be diprotic. In this case is HCO3. Okay. So let's look at this practice exercise. So we have 40 milliliters of solution of sodium hypochlorite. So we're starting with a salt. So hypochlorite. So this is ClO, sodium hypochlorite. And it's titrated with a strong acid. So now we have, this is sodium hypochlorite. So let's look at this one. ClO minus will contain sodium ions and ClO minus ions. So again, the cations, you add OH. So the parent is going to be, actually should be going the other way. So this comes from the reaction of sodium hydroxide, and then, I don't know what happened to that. Let's try it again. Sodium hydroxide. And the other parent is going to be H, rather H, I add H2ClO. And so this is not one of the 6 strong acids that you're supposed to know. So then you're going to say this is a weak acid. You know all the weak acids if you know the 6 strong acids. Everything that is not acidic and not one of those 6 is weak. So this is a weak acid. So, and this is its conjugate base. So this sodium is neutral. So the salt is going to contain a neutral ions and basic ions, so it's going to be basic. And that makes sense because it's being titrated with HCl, it's titrated with an acid. Okay. A solution, select the appropriate indicator. So what we need to do is know the pKa, the pKa or the, so we need to actually find out what is going to be the pH at the endpoint. So let's go back to this titration curve that we're looking at. So we have a weak base, like we had in here, and the pKa is going to be the midpoint. This one is going to be the endpoint. So we need to know what is going to be at the endpoint. And at the endpoint, you only have, for these two, only the salt is present. Why? Because at the endpoint, all the acid, the amount of acid and the amount of base have neutralized each other. So you only have the salt. So in this case, in this case down here, let me switch to blue. This case down here, you will have NaCl. In this case up here, and we'll make it in red, you will have NH4Cl. So you have only the salts. Only salts present. So if that is the case, then we should be able to figure out what the pH of the salt is based on the Ka. They have given us the Ka? No. We're given the initial concentration and volume of basic salt solution and the concentration of HCl. So let's write the reaction. The reaction that is going to happen, oh yeah, it's here. Sodium hypochlorite plus HCl is going to give us NaCl, which is neutral, and HClO aqueous. So that will be Sorry, here's missing an arrow here. And NaCl aqueous, this is neutral. So that's meaning it's not going to contribute to the pH. If that will be the only salt, it will be 7. But this one is acidic. And that's what it will be formed at the end point of the titration. And so if that's the end point of the titration, we can figure out what the pH is for this solution here. We know how much sodium hypochlorite was this here. We know the volume. We know the molarity, so we can calculate the moles of HClO4. So we know how much is this, and the ratio is 1 to 1. So if we know the moles of this, we will know that'll be the same as the moles of the HClO, and therefore we can calculate what the pH is by using the Ka. So we can take the HClO, so amount, which is 0.05. Let's see what they calculated in here. Nope. So it's 0.05. Ah. Okay, so why is it 0.05? I was thinking. Okay, so you have 0.1 molar of the base, and you have 0.1 molar of the acid. So the ratio is 1 to 1. Again, here, let's make it in blue. This is 1 and 1 of the base, 1 of the acid. So you're going to use exactly 40 milliliters of this amount. Why? Because you have the same concentration for both the acid and the base. And since you have to add equal amounts of acid and base, and they have the same concentration, you have to add equal amounts of HCl, which means you're going to consume 40 milliliters of HCl used. So that means that you're going from 40 milliliters to 80 milliliters, and the initial concentration is 0.01. So we know the moles, but the solution is going to be twice the volume of the initial solution, which is 40 milliliters. It's going to turn into 80 milliliters. So instead of being 0.1, you're going to be 0.5 initially. So we're going all the way to let me go back to the curve. We're going all the way here. And so we know that we would have used another 40 milliliters in that case, not 20 here, but 40 milliliters in our case. And so that means we have the 40 milliliters that we started here. This is 40 milliliters of the solution that we started here. And we're adding another 40 milliliters, that is 80. And therefore we have half the concentration. So instead of 1.1 molar of the product, we only have 0.5 molar of the product. Remember that this rice table, these are molarities and not moles. And it's very easy to get confused. Sometimes I get confused and work in moles. This has to be moles divided by liters, always. Always. And therefore, you are going to do that. Okay, so next time we're going to look, I'm sorry, I went over time, so I apologize. So next time we're going to look at these calculations in more detail. This very last practice exercise, we'll start here and we'll go on to look at all these subjects next time. Okay, great. Thank you for your time. Are there any questions before we call it a day? Okay, great. So I'll see you next week. Okay, let me stop recording.